Okay, so a super quick homework hint on problem 51. In this problem, we have two different types of materials. On the inside, here in green I've drawn, we have a solid sphere that's a non-conductor. So with a non-conductor, the charge is going to be spread uniformly through the whole volume. And then we have some empty space in between. So between radius A and radius B is empty space. So we're going to assume that there can't be any charge in the empty space. And then between radius B and radius C, we have a thick shell that is spherical and is made of a conductor. Right. So with a conductor, then we know that the electric field. We automatically know that the electric field within the conductor is equal to 0, and from that argument, we know that all of the charge has to be on one of the surfaces, or distributed either on the inner surface or the outer surface. There could be some in each place, right? So when we think about within the some radius within this non-conductor, right? We need to know how much charge is inside of that. So we're given a total charge Q1. We need to know what fraction of that charge, or how much of that charge is within that Gaussian surface if we're inside of the non-conductor. Right, so we know that the charge density is the total charge that's on this volume divided by the total volume of that sphere. Right, so we can call that V total. And then when we want to find Q enclosed, it's just the charge density times the volume of the Gaussian sphere, right? Because it's what's inside the Gaussian sphere that counts. Okay, so for that one, for that stage, and then of course, everything that has to do, if we're in here or if we're in this empty space, right, nothing that the conductor is doing matters at all in terms of calculating the electric field because it's outside of our Gaussian surface. That's the great thing about Gauss's law when we have this kind of symmetry. Okay, so then when we go outside of here, now we need to know how this charge, which is -2 times the charge here, is going to distribute itself. And the fact that allows us to say anything about that is that we know we draw a Gaussian surface anywhere in here, and I'm going to draw a sphere just for convenience. We know that the electric field is 0 everywhere on there, so that tells us that the flux is 0, and so we know that the total enclosed charge has to be 0. Okay, so I don't want to do the whole rest of the problem there, but that should get you started. Okay, so then once you know how that charge distributes itself, then when you're looking at the electric field at various points that enclose either the inner surface or the outer surface or both, then you can use that information to do Gauss's law to find the electric